Okay, folks, here is our flipped classroom for those who missed it. It's a four-part problem using the equation, the thermite reaction, that 2 aluminum and iron oxide goes to aluminum oxide and 2 irons. The first question simply asks you what is the enthalpy of this reaction. To do this, the enthalpy of reaction, you need your enthalpy of your relative reactants and your enthalpy of your products, and that is conveniently provided for us in the table beside us. Let's go to the doc cam so we can solve this. Okay. So, enthalpy of reaction is, simply put, the sum of all the products, minus the sum of all the reactants. All of our products, we have 1 aluminum oxide and 2 iron oxides. Unfortunately or fortunately, the enthalpy for a pure element is 0. So 2 times 0 is 0. We're subtracting the enthalpy of all of our reactants. All of our reactants, negative 824.2, and we're adding the 2 times 0, and 2 times 0 once again is 0. So we're subtracting, essentially, we're taking 1675.5, and we're subtracting a negative 824.2. And you get the enthalpy of reaction is negative 851.3 kilojoules per mole of reaction, or per mole of iron oxide. Every time I run this reaction as written, one time I generate this much energy. So per mole of reaction, or kilojoules per mole of Fe2O3. That's one way to look at it. Okay, so the problem 2. Given the above reaction calculates the enthalpy per mole of iron oxide, how much energy could be generated if 120 grams of aluminum reacted with excess iron oxide? The molar mass of aluminum is 26.98. So we're going essentially grams of aluminum to moles of aluminum oxide. Grams of aluminum to moles of Fe2O3. Well, we said we start with that. Well, if the molar mass of aluminum is 26.98 grams of aluminum per 1 mole of aluminum, where would I get these numbers? Periodic table. What have I done? I've provided said numbers so we don't have to go to the periodic table, but that's where they're from. So that is the moles of aluminum. And then for every 2 moles of aluminum, we would get 1 mole of iron oxide. So 120 divided by 26.98 divided by 2 would give us 2.2, we'll say 224 moles of iron oxide. So with that in mind, for every 1 mole of iron oxide, we get 851. So 851.3 kilojoules per mole of iron oxide. If I use 2 and then some moles of Fe2O3, then I'm going to figure out how many kilojoules we would produce totally. So I should produce negative 1893.18 kilojoules total. Now, wrong thing. So the third question, how much iron could be generated from that same amount of 120 grams of aluminum? So this one is just the straight up grams to moles to moles to grams. So we're taking we'll see, we're taking our grams of aluminum to grams of iron. Set things up like normal. 120 grams of aluminum, 26.98 grams of aluminum per 1 mole of aluminum. Our balanced chemical equation said that for every 2 moles of aluminum, we got 2 moles of iron. Grams, moles. And the molar mass of iron, which I got and provided for you from the periodic table, 55.85 grams of iron. Diagrammed out where I want to go. Canceled out all my units except for the unit of what I want to get to. Now it's just a matter of punching it into my calculator. 20 divided by 26.95, Now I could leave off the 2 over 2, or I could put in the 2 over 2. It simplifies itself, but the calculator can do that for us if we don't realize that. We do that, and we get the mass of iron is something like 248.406 grams. Now, the last question is, considering the mass of iron we just formed, and considering the energy that we produced, if the iron were to absorb all of that enthalpy of reaction, by what temperature would the metal change by? So it's simply a Q equals mc delta T. I give you the specific heat capacity of iron as being 0.4494 joules per gram degree C. So with that in mind, the Q of the iron is going to be negative the Q of the reaction. So the negative 1893.18 is going to be positive 1893.18 for the iron. We already have the C of the iron. We have the mass of the iron right there. Now the only problem is that this is kilojoules. So, and this is joules. So we have to turn that into joules. So there's 1,000 joules in 1 kilojoule. So we get something like 1893180 joules of heat absorbed. That is going to be equal to the 248.406 grams of iron times the heat capacity 4494 joules times the delta T, which is what we're solving for. We're solving for our delta T. So we have to take both sides and divide it by our mass and divide it by our C, and that will give us our delta T. So 1893180 divided by my 248.406 divided by 0.4494. If I do this, I get a ridiculously big number, and that's fine. 16,958.86 degrees. So if that iron were to absorb all that temperature, it would go up by close to 17,000 degrees. However, the actual number is not quite that high because aluminum oxide is also formed. Aluminum oxide absorbs a lot of that temperature. It has a higher specific heat, so it takes more energy to warm it up. But it's still along the lines of like 7,000 degrees or something crazy like that. So it absorbs a lot of heat. And that right there is that flipped classroom.